Welcome back to NE 630, Introduction to Nuclear Reactor Theory. Last time we discussed the compound nucleus formation and how the nuclear reaction will proceed once the nucleus will absorb the neutron. So let's just continue what the business that we were doing last time. So let's assume that I will give a for the compound nucleus. So let's assume that we have a neutron here is moving towards a uranium-238 92. Then the neutron will be absorbed, and then we will make the uranium-239 92. Again, this is a transitional state, and this is the compound nucleus. So let's assume that uranium-238, the ground level for uranium-238 92 is here, and the incident neutron come with kinetic energy equal to 6.67 electron volt. So this is E kinetic equal to 6.67 electron volt, and this is the incident neutron. So the energy of the incident neutron above the ground level of the uranium-238 is this amount of energy. Once the neutron will be absorbed by the uranium-238, it will form the uranium-239 nucleus, and this is again a transitional state. Then we will have several energy level in the compound nucleus. So the difference, this is the 6.67 electron volt. This difference usually is the binding energy of the last neutron inside the compound nucleus. So the excitation energy will be somewhere here. The neutron can go either directly to the ground state by gamma rays, or it can go to, let's say, intermediate state by emitting gamma 1, then to the second level by emitting gamma 2. So if you have the cross section, sigma, gamma is represented in the x-axis here, and in the y-axis is the energy. You'll notice that you will have the cross section is just the probability of interaction of the neutron with the nucleus. So if you have it something like this, maybe you will have something like this, then at this level you will have the cross section goes up to a very high value, then drop in between and high value and drop, and so on. So this type of behavior is what we call a resonance. Why it's called resonance? So it's exactly like the resonance in electric circuit. When you have electric circuit composed of capacitor, inductor, and a resistor, if the capacitance, the resistance, or the impedance of the circuit is minimum, when it is minimum, it will be minimum when the capacitance is equal to the resistance, but because one is leading by a 90 degree, the other one is lagging by a 90 degree, they will cancel each other, and you will have only the resistor that's remaining in the circuit. In this case, the circuit will be called a resonance circuit. So if you adjust and tweak, play with the frequency of the circuit, the frequency, if you change the frequency, for example, you will notice that you will come up to the point where the XL will cancel XC, and you will be remaining only with the resistance, and this you have a maximum current flowing into your circuit, and this is called resonance. You are in resonance. So this is exactly the same. If the energy of the binding energy of the neutron inside the nucleus plus the kinetic energy meets one of those energy levels, inside the nucleus, the nucleus is called in a resonance. What does it mean, a resonance? The reaction or the probability of interaction with the nucleus is high. So there is a big probability that the nuclear reaction will take place. It's exactly the same like if you think about the atomic shells. So if you give the electron energy, which is not sufficient to raise the electron from the energy level where it is hanging around currently to the next one, the electron will not take the energy. But if the energy is sufficiently, which is the difference between the two levels, the electron will take the energy and jump to the second level. So this is like exactly the same concept. So this is the resonance here. And if you look at this resonance, and in a minute I will be showing you the PowerPoint presentation for several types of cross-section with resonances and so on. This resonance, usually, there is a very nice formula. This is called, by the way, this is called radiative capture reaction. So this is called radiative capture interaction. Why it is radiative capture? Because the nucleus will capture the neutron, then it will emit gamma ray. And this is called the radiative capture. So bunch of those radiative capture interaction are very important. This one, more specifically, is very important in our nuclear reactor because uranium-238 will absorb it, then it will emit gamma rays, then it will have a beta decay, then it will have another beta decay, and then it will transform to plutonium-239. And this is the way we produce plutonium in nuclear reactors. In fast breeders, usually, you put a blanket around the reactor where the blanket will be mainly uranium-238, and because of the neutrons bombarding this blanket, you will transform most of the uranium-238 to plutonium-239. So if you do fuel processing for your fuel, spent fuel, then you will notice that you not only have actinides and fission products and so on, but also you have transuranic element from such reactions. Transuranic mean elements beyond uranium. You started with the uranium from the beginning, but you have transuranic action from those types of reaction in the gamma reaction. So there is a formula that represents the resonance. This resonance, how the resonance look like in the vicinity of the resonance itself. So the cross section, how the cross section look like in the vicinity of resonance. This formula is deduced by Bright-Wigner formula. And the Bright-Wigner formula, it's assumed that this is isolated resonance. We will see in a minute what do we mean by isolated resonance. So this is sigma of energy E, and this is energy E, and this is gamma. So let's assume that we have in the cross-section one of those isolated resonance. In a minute, I will show you that in the cross-section, if you look at the cross-section for uranium-235 or uranium-238, you will notice that the cross-section is smooth in certain energy region. Then you have very intense cross-section. Those called overlapped resonance. The resonance are overlapped and very intense region of resonance. They are not isolated, so you cannot isolate one single resonance like this. Extremely overlapped. And this is why, because for heavy element like uranium-238, those energy levels that I am showing to you spaced are very, very small and very adjacent to each other, very condensed. This is why you have this very condensed resonances. But for the light elements, like oxygen, for example, you will notice that the energy levels are apartly spaced. So you will have, if you will have resonances, for example, maybe you will have isolated resonances in the cross-section. This is, when you look at the cross-section, you will know this. So this is an isolated resonance. The maximum of the resonance here is at E naught, for example. So Bright and Wigner, they represented the radiative capture cross-section, sigma, gamma, at energy EC. So sigma, the radiative capture cross-section at energy EC. EC here is any energy of the neutron in the center of mass system. So there is two representation for the energy of the neutron. If we are looking from a firm frame of reference, we will be looking at what we call lab system. And this we'll be studying in a couple of lectures. But if we look at the neutron and the target, in this case the uranium-238, in another frame of reference where we are looking at the center of mass. So what do you mean by center of mass? Center of mass is a virtual center where if you get the average, let's say average position, average over mass of the position of the two particles. So the position of the neutron and the position of the nucleus. So they are approaching each other. The neutron is tiny with respect to uranium-238. It's 1 over 238 of the mass of the uranium. So the center of mass will be closer to the bigger mass. So if you just write this center of mass and look for both particles, the interaction will be extremely simplified as opposed to if you are just sitting in the lab looking for the neutron and the mass approaching the uranium-238 approaching each other. So there is two treatment for the mechanics or the classical mechanics problems. One, if you ride on the center of mass and look for both particles, and the other one is if you sit in the lab. So this energy here, as you see, is the energy inside the center of mass, not in the lab. So this is why we said EC. So this is called, so this is E naught, sigma naught, which is sigma add the energy E naught is called sigma naught, multiplied by gamma gamma over gamma, multiplied by energy E naught, divided by EC to the power of 1/2, multiplied by 1 plus y square, and y is nothing more than 2 over gamma, multiplied by energy EC minus E naught. So EC, E naught are neutron energies in center of mass and at resonance. So the neutron energy in center of mass at any energy, which is EC, and at the resonance energy, which is E naught. This is the neutron energy. Gamma is called radiative width. What do we mean by radiative width? Radiative width, the energy level inside the nucleus will have certain width. Any energy level here will have certain width. And this width, usually we call it gamma. And what's this width? Usually it's delta E. If you remember, how many of you took any course in modern physics and know what's the Heisenberg uncertainty principle? Do you remember Heisenberg uncertainty principle? So the Heisenberg uncertainty principle states that delta X dotted with delta V is greater than or equal h bar. Yes? And delta E dotted with delta T greater than or equal to h bar. It's less than or equal, I think. Less than or should be less than or equal h bar. What does it mean? For the first one, means that if you want to look at a particle, if you define the particle location within delta X, you said that this particle is within, it is between X and X plus delta X. Then you cannot indefinitely define the momentum of the particle. You cannot say, oh, I know the momentum for sure. The momentum is this plus or minus 0. You cannot say this. So you have to follow this rule. If you said that, okay, the inaccuracy in determining the neutron location is 0, this means that you do not know anything about the momentum for the particle. The inaccuracy in determining the momentum is infinity. Why? Because 0 multiplied by infinity should give you some certain number. But if you get 0, anything multiplied by 0 is 0, so you cannot get this number. So this is the uncertainty principle. If you just change delta X, which is delta X has a relation with energy, and delta B has a relation. If delta B has a relation with energy, and delta X has a relation with time, you will notice that you will obtain this formula. What does it mean, this formula? It means that, okay, if I knew for sure that this is the energy width, I will know how long the duration the particle will be stationed in this energy level. So if this energy level is very, very small, this means that it will, let's say, it will stay there for a very long time in order to multiply very small by very long, and it will give you a constant, and vice versa. So this is delta E is what we call the energy level. So it tells you the energy level, how long you will stay in this transition state, how long you will stay in this energy level. So gamma is the radiative width, and if the total width now, what does it mean, radiative width? It means that you might come to this energy level and you emit neutron, you emit alpha particle, you emit beta, you emit whatever reaction that will take place. So if you come to this energy level, there is gamma for gamma, there is gamma N for neutron emission, there is gamma P for proton emission, and so on. So gamma is the radiation, gamma is the radiative width, but gamma is the total width, is the width of all the interaction that can take place at this energy level. So if you divide gamma by gamma, this is a measure of radiative capture probability. So this is the probability that the compound nucleus will decay by gamma rays. Again, gamma N over gamma. This is again probability that compound nucleus will decay by neutron emission. Did you understand? And so on. So this is just what we mean by this formula. So the formula states that, okay, the cross-section sigma gamma, the radiative capture cross-section, as a function of energy in the center of mass system equal to certain sigma naught multiplied by the probability that once the compound nucleus will be excited to this level, it will radiate by gamma radiation, multiplied by the energy E naught over EC multiplied by 1 plus y square. So if you look at this, if the energy EC, the energy of the neutron in the center of mass system, is equal to E naught, so this term will be what? Will be 1. And then this is EC minus E naught is what? 0. So this will be what? 1. This will be 1, and this will be 1, and this will be just the probability. This is the total cross section here multiplied by the probability of radiative capture. So did you understand? So now let's assume that this is just for a monoenergetic neutron. But what happens if we have a distribution of neutron energies, not a monoenergetic? And this is exactly the case where we have the neutrons inside the moderator. Last time I showed you the distribution of energy of, yes?
What was just regular gamma without the sub-gamma?
Gamma is the total width. So this is, the gamma is the width for just one type of interaction, which is the radiative capture. Gamma total will be equal to gamma plus gamma neutron plus gamma neutron prime plus gamma alpha and so on. So it's just the width for the rest of the interactions. So let's assume that now I have a Maxwellian distribution for the neutrons. Where I got the Maxwellian distribution? When the neutron will have the energy required to do the nuclear reaction at very low energy, it gets the Maxwellian energy distribution from the thermalization. So there is two processes that took place in the nuclear reactor during the fission times and after the fission times, and we will study this during this course. So neutrons are getting out from the fission with chi distribution, the one I showed you last time here. Then they will start moderation, and this moderation is just the billiard ball collision between the neutrons and the rest of the fuel, as well as the moderator. The fuel, usually the masses of the fuel, it's like a big ball, and you have a small marble. You hit the marble with the ball. You hit the ball with the marble. It does not lose anything. So the main energy loss will come from the moderator, and this process of losing all the energy from the fission up to 1 electron volt is called moderation. And there is moderation without absorption, and there is moderation with absorption. Once you reach 1 electron volt, which is the cutoff for the thermal energy region, you will start exchanging energy with the medium, which is in this case the water, and we will have an equilibrium. And this equilibrium is called Maxwellian. Of course, it's not perfect Maxwellian because of the absorption at very low energy. It will shift the Maxwellian toward the high energy. And this is called absorption hardening. And we'll look at this in details also in future. So if we have, instead of just one energy, like a beam, this is for a beam with one energy. Let's assume that we have a Maxwellian now with energy. So in this case, I will have an average for the sigma, and this is the energy of the neutron. Now this is the temperature. Why? Because the Maxwellian is defined by a temperature, and if you change the temperature, the Maxwellian distribution will change. So this average is coming from where? It's coming from 1 over the velocity as a function of energy E, and this is just the energy E multiplied by V of E minus V of E prime multiplied by sigma as a function of EC multiplied by the Maxwellian or whatever energy distribution function as a function of E prime and T. What does it mean? You remember last time I talked to you, I told you that the intensity is equal to N multiplied by V. Yes, NV is intensity. And if you multiply intensity by sigma, by the cross section, will give you what? By total sigma. If you remember, what's this? Sigma phi. Always remember this. Sigma phi is the total number of interaction per centimeter cube per second. Interaction density. Total number of interaction per centimeter cube per second. If we have one nucleus, so this will be what? Sigma, because we have N equal to what? 1. And this is N multiplied by V. If we have one neutron, this will be what? Sigma V. So this is the number of interaction per centimeter cube per second in case of we have one nucleus and one neutron. Yes? This is just this one. So if you multiply sigma average multiplied by V of E, this is the total number of interactions. But this is the average. Why? Because now sigma of EC multiplied by the difference in velocity between the neutron and the projectile multiplied by the distribution function will give me the average. And this is just an averaging process. Like when I talked to you last time, I said if you have a distribution function f of x and you want to get the average for x, what you will do? You multiply this by x and you will integrate from x equal to negative infinity to infinity, and this will give you the x average. Yes, this is just a statistics, 101 statistics for continuous distribution, not for discrete. And because the energy here is a continuous distribution, so we do the same. Here is the distribution function, and I want to average what? I want to average sigma v. So here is sigma v. Okay, did you understand? So this is just a normal process of getting the average sigma. But now, instead of having the gamma radiative capture as a function of energy of the neutrons, I have the cross-section is a function of energy of the neutron plus the temperature of the distribution, because now the interaction is dependent on the energy of the distribution. So T is the temperature, of nuclei. So this is the temperature of the nuclei, the water in this case, or the absorber. And E prime is just the nuclei energy. And E is the neutron energy. Why? Because if the neutron is coming here, and let's say the nuclei of the medium, at the very early beginning, this is the case where the medium has just a stationary nuclei inside the medium, and the neutron is hitting those stationary nuclei. Now, if you have a nuclei like water, and the water has temperature, so what will happen for the nuclei of the medium? They will start jiggling around the center of oscillation. So they will start jiggling around. And now, if you are hitting two billiard balls, the target is this billiard ball. Instead of just a sitting target like this, it's a target like this. So if you are hitting target like this with another target, what will happen? The interaction will depend on the velocity of this jiggling around nucleus, and this is what we see here. This is why we get the difference between the two velocities. Do you understand? So if f of E is a Maxwellian, now we can represent f of E. This is for any general f of E, any general distribution. So if it is Maxwellian, so f Maxwellian as a function of E prime is equal to 2 pi divided by pi. K is a Boltzmann constant divided by T to the power of 3/2 multiplied by the energy E prime multiplied by e to the power of E prime over KT. Again, this is K is just Boltzmann constant, and as I remember, 1.38 10 to the power of minus 23, as I remember. Okay, T is the temperature, and pi is the ratio for the perimeter to the radius. So sigma gamma as a function of E and T. Now, this is for any sigma. If we replace this formula, we replace sigma here by sigma gamma, which is the radiative capture cross-section given by the Bright-Wigner formula. I just erased it from the blackboard. If I substitute here with sigma gamma, and I substitute here with the Maxwellian distribution, and perform this integration, I will reach to the value for the radiative capture when I have a medium with a Maxwellian distribution in energy, and this will be E naught over E. So it is up to here, it is exactly the same like the previous Bright-Wigner formula, but I have a new function called psi, like this. So this function is just equal to and x in here is just 2 over the total width multiplied by E minus E naught where A here is the atomic mass number. So again, I do not expect that you memorize any of this. Yes?
Psi of eta and x, or eta and chi?
Zeta psi of zeta and x. So the X is here. Not chi, this is X. I do not expect that you memorize this, but I want just to tell you the things that you will take out is how we will represent an individual resonance, which is called isolated resonance. If the resonance is for a stationary nuclei, it will be represented by the Bright-Wigner formula. If the nuclei of the medium has a Maxwellian distribution, then we will do this averaging process, and this is the cross-section for the Bright-Wigner formula once you have a Maxwellian distribution, and those are the definition of the parameters inside the formula. This is just what you want to take out. So if, let's say, if you are working as a nuclear designer in a company, if you want to correlate this to industry, for example, if you will work as a nuclear designer in a company, then you have to do the cross-section preparation if you are doing core calculation. So core calculation will have what we call cell calculation, then core calculation. Before you do the cell and core calculation, you have to prepare the nuclear cross-section data libraries. And in those nuclear cross-section data libraries, you have to calculate what is the resonance cross-section, because it's very important. In reactor calculation, resonance calculation are very important. So how you will know to do the resonance calculation? You will do this resonance calculation at, let's say, you will say the fluid or the moderator in the reactor will be water at 300 degrees, for example. So you'll calculate the resonance, the radiative capture cross-section from here. Of course, this will be done by modern day computers, and you will not do, but you have to understand the physics, how this come into play. So this is one of the models, for example, for calculating radiative cross-section and so on. We will not visit this in details, except for chapter, I think, 5 or so. Yes, go ahead.
In e to the minus 1/4 x minus y, is the y defined as we did before?
As we did before.
Okay.
Yes, as we did before.
Thank you.
So for the neutron emission, this is for the radiative capture. For the neutron emission, if we have neutron emission reactions, for example, there is several types of neutron emission. There is N, and this usually we call it elastic scattering. And there is N prime. This is, we call it inelastic scattering. There is N, 2N, and N3N, and so on. Of course, when you go N to N and N3N and N4N, this means that the neutron will come into the nucleus, inside the nucleus, will give the nucleus the binding energy. No matter what's the energy, kinetic energy of the neutron, the binding energy will be the same. The only difference will be what? To bring into the table, which is inside the nucleus, will be the kinetic energy. So if you have a zero kinetic energy, you will give just the binding energy. If you are coming with a very small amount of energy, so you will give just the kinetic energy, which is very small, and the binding energy. If you are coming like a bullet or train inside the nucleus, so we will shatter the nucleus. And this is why, because your kinetic energy plus the binding energy is so high that you can distribute the total energy giving to the nucleus over so many particles, and you might give, there is a very big chance that you might give the nucleus very high energy, that you impart 2 neutrons or 3 neutrons or 5 neutrons. But the energy, once you go up, you need very high energy, kinetic energy to those types of reaction. So usually we write the reaction as XZA plus the neutron, and this will give us XZA plus 1, because you added 1 neutron inside, and this will decay to XZA minus 1 plus 2N. And usually we write this types of reaction as XZA N 2N XZA minus 1. Of course, there's, again, for the neutron-induced, all those types of interactions are called neutron-induced nuclear reaction. Neutron-induced nuclear reactions. So we might have N3N, again, might have NP, which is proton, we might have N-alpha reaction, and so on. So there is lots of interactions. Now, we wrote the Bright-Wigner formula for an isolated resonance for the case of radiative capture. What will be the shape of, of the inelastic or elastic scattering cross-section? The elastic scattering cross-section will be a little bit more complicated. So for elastic scattering, again, when the neutron will interact with the nucleus, and the neutron will come out with the same energy, and it will not leave the nucleus excited, we call it elastic scattering. Even if the neutron will get inside the nucleus, then it will raise the nucleus to a certain energy level and then get out and leave the nucleus again in the ground state. This is called elastic scattering. So the elastic scattering, if we look at the elastic scattering cross-section, we'll notice that sigma scattering of energy EC in the center of mass, it's composed of three components. One is, now I have gamma N instead of gamma gamma. Why? Gamma gamma was for radiative capture. You capture the neutron, you do not emit anything. Here you capture the neutron and you emit a neutron. So this is gamma gamma. And this is multiplied by E naught divided by EC, all to the power of 1/2 plus. So what's this? This is exactly the same like Bright-Wigner formula, but for what? For gamma N instead of gamma gamma. So this is just compound nucleus formation. So this term is coming from where? Neutron gets inside the nucleus will form a compound nucleus and then emit the neutron. Okay, there is another term which is here, 4 pi r square. What's this? What's 4 pi r square in geometry?
Surface area.
Surface area of what? Sphere. So this is the probability that the neutron will hit the nucleus. It will not get in, but it will see the nucleus as a billiard ball. And this is the cross-section coming from the geometrical radius of the nucleus. So just the nucleus is sitting in there, and the nucleus will not see the internal structure of the nucleus. It will see it as if it is a ball, and it will try to hit it. So if the neutron comes within this 2r, so it will interact. If it comes out, it will not interact. So there is a probability of forming the compound nucleus. There is a probability coming from what? From what we call shape or potential scattering. So this is called potential. Potential, sometimes they call it shape because of the shape of the nucleus, scattering. And this is what? Compound nucleus, and this is the Bright-Wigner. And there is interaction between both. Interaction term, and this interaction term has sigma naught square r divided by lambda naught multiplied by y plus 1. And this is called interference term. So this interference term is coming from quantum mechanical effect. So I will not go through it. So this is the nuclear radii. And I just told you at the very early beginning, the first lecture, that is given by 1.25 10 to the power of minus 13 A plus 1/3, and A is the atomic, where A is the atomic mass number. Atomic mass number. And 4 pi r square is just the potential scattering term. So again, if you do the same, this is if the nuclei of the medium are stationary, there is no distribution for the nuclei of the medium. What if the nuclei of the medium are jiggling because of the temperature? Now, so we have to do what? We have to average over the distribution energy of the nuclei of the medium. In this case, if the nuclei of the medium are a Maxwellian distribution, we have to integrate over the Maxwellian distribution. And if we integrate, so this is for stationary nuclei for a distribution of nuclei energies, a distribution of nuclei energies, it will be sigma scattering energy E and temperature T equal to sigma naught gamma n over gamma multiplied by chi of zeta and x plus 4 pi r square and chi of zeta and x is given by zeta over square root of pi negative infinity to plus infinity y e to the power of minus 1/4 x minus y square y all square multiplied by zeta square divided by 1 plus y square dy. And lambda just is the de Broglie wavelength, which is given by the momentum h over momentum, h bar over momentum, or h over momentum. So this is the characteristic wavelength h over p for the associated wavelength for the particles. So now we got to know so far that one of the mechanisms for forming for the nuclear reactions to take place is the compound nucleus formation. We study what do we mean by compound nucleus formation. Neutron will get inside the nucleus, will give it the binding energy plus the kinetic energy. If it hits the binding plus the kinetic hits one of those energy level, you will be in a resonance. How to represent the resonance? Bright Wigner gave us the idea. They wrote their formula, but this was for a stationary nucleus. If the nucleus is in a distribution of nuclear energy because of the temperature of the fluid or so on, we have to take this into consideration. We have to average over the Maxwellian or whatever distribution we have in hand. Now, if we look at the cross-section, usually we write the total interaction cross-section as sigma total, and this will be sigma gamma plus sigma fission, the probability of gamma, probability of fission, sigma n prime, which is the inelastic cross-section. And the elastic cross-section, we do not write it. Sometimes people write it as sigma n, or people write it as sigma s, which is just the elastic scattering. So this is called sigma total. And of course, if you have sigma alpha and sigma whatever, so you have lots of interactions, so plus blah, blah, blah. So there is another term called non-elastic. So differentiate between two cross-sections. One is inelastic. What's the inelastic? What's the elastic collision? No net energy giving to the nucleus. So the nucleus is not excited. What's the inelastic? The nucleus will be excited. What's the non-elastic? The non-elastic is everything minus the scattering. Did you understand the difference? So there is inelastic and there is non-elastic. The non-elastic is all the cross-section minus the elastic scattering. So everything but the elastic scattering is the non-elastic. But the other one, the inelastic, is just the interaction where the nucleus will be left. It will emit the same one of the neutrons with different energy, and it will leave the nucleus in an unexcited state. Did you understand the difference? Now, let's move on and show you some of the cross sections before we Did you see it right now? Okay, so if we look here, this is the cross section for uranium-233 fission cross section. This is called material number equal to 18. This is just a definition for each one of the materials like uranium and so on. And this we will find it in the nuclear evaluated data libraries usually. By the way, if you want to look for any cross section, just in Google write National Nuclear Data Center. National Nuclear Data Center, and just log in and you will find the table of isotopes which will have everything. So we will need during this course to go and visit this National Nuclear Data Center to fetch some of the cross-section which are of importance for the homework or any other projects, for example. So here is the cross-section, and here is the energy, neutron energy. And this is, both of them are in logarithmic scale. And as you will see here, this is something like a line. So if you have a line in a logarithmic scale, this means that the cross-section will go like 1 over E. So because if you take ln E will give you just a line. Yes, with E. So this means that the cross-section goes like 1 over E here, 1 over E, or maybe 1 over V cross-section. And again in this area here, and then from something like 1 electron volt, which is the cutoff for the thermal energy region, the cross-section will have unresolved, this is called unresolved resonance. It's not isolated, you cannot resolve those resonance, very intense as you see here. And this is just the fission cross-section for the uranium 23392. And they are dominant from anywhere from 1 electron volt to 100 electron volt. This is a fissile material, uranium-233. But again, the abundance for uranium-233 is null. Usually it's null, and usually you produce it from thorium-233. So if you look here, this is the cross-section for uranium-235. And again, you'll notice that there is 1 over E behavior. It's 10 to the power of 3 barn, while the other one was 10 to the power of 3. So they are similar, more or less. Then if you look here, this is 1000 barn, which is a good cross-section, very high cross-section. Then if you look at something like hundreds of milli-electron volt or so, couple of hundred milli-electron volts, you see it's hump like this, then one isolated resonance, then very unresolved, very high unresolved resonances up to 1000 or 2000 electron volt. So usually the nuclear fission will take place at very low energy, at 0.025, 25 milli-electron volt. They are dominant. And this is also, there is also fission that took place up to 1 kilo electron volt energy. But the cross-section drops from 1000 barn to something like 1 barn, beyond something like 1 kilo electron volt for the neutron energy. So if you look at plutonium-239, so all those are fissile isotopes. Plutonium also 1000 barn. Then you have this one single isolated resonance. Then you have those resonances here, but those resonances are from 10 electron volt up to 1 kilo electron volt, and so on. So if you look now for uranium-238, uranium-238, now it is even nuclei. So even nuclei, we said that for even nuclei beyond 90, Z equal to 90, the fission cross-section, you can fission those isotopes, but the fission cross-section is what? Is a little bit high, and it requires very high amount of energy to fission the nucleus. And this is what we call the cross-section, the threshold energy for this types of interaction. So you will notice that you have some isolated resonances up to 10,000 electron volt. Yes, but the resonance really does not trigger until, because this is what? This is 0.1 millibar, which is very, very small. very small. So if you want to see again some appreciable interaction or appreciable fission, it's beyond 100 kilo electron volt, 100,000 kilo electron volt. So usually 100,000 kilo electron volts, you jump up to something like 1 bar, which is still very small, and it goes like steps. If you look at this up to 10 to the power of 10, you'll notice that it goes up to steps. So this is why the uranium, excuse me, uranium-238, it has a threshold and does not fission at thermal energies. If you look now at plutonium-240, and this is the cross-section for the fission cross-section for plutonium, again, still 100 milli, which is still small, and still you have something like one resonance here and a couple of isolated resonance, and you go back again to one bar. Now, if you look at the fission cross-section, for example, for several of the non-fissile, which we call it last time fissionable, thorium, uranium-238, uranium-236, uranium-234, plutonium-242, all of them have the threshold energy here. So lastly, I will be just focusing on two. I have a minute maybe. If anybody wants to leave, if you have classes, you can leave right now, but I have only 1 minute. So this is just what we call the yield for the fission. What does it mean, the yield for the fission? So if you have a nuclear fission reaction, and one of the fission will be giving you similar masses. So uranium-235, it gets 1 neutron, so it is uranium-238 now. The 236, the compound, divide by 2, it will give you whatever the two masses. Those two masses are equal. So you said, okay, how many of those nuclei that went into the fission? I have million nuclei. How many have similar or symmetric fission? How many have a mass of 120 and a mass for 60? How many have this and that? So you start collecting those total numbers, and you divide by the total number, which is a million, and this will give you the yield. So here in this area here, this is a symmetric fission. So if you split the nucleus, you'll get 2 equal masses. But this is not the most probable. The most probable, if you will do the fission at those 2 peaks. So the most probable that you will get krypton and barium. And krypton is 136 or 138 or whatever, and barium is 80 something here. So this is the neutron yield. And it shows the neutron yield for thermal neutrons, the fission yield for thermal neutrons, and for 14 MeV neutrons. For 14 MeV, the nuclear yield, the fission yield, become more and more symmetric, because you come with very high energy neutron that does not matter. It will knock the nucleus and split it to 2 equal pieces. The last one is just the total number of neutrons emitted per fission, and this shows you that the total number emitted per fission for uranium-235 is around 2.45, but for plutonium-239 it's a little bit more, 2.9. Once you increase in energy, there is a pretty much good chance that you will produce more neutrons per fission when you increase the energy, and both of them will go linearly with each other. So thank you so much for your attention, and we'll see you next week, and have a good weekend.